Alright, so let's continue with our word embeddings. This was our formula to predict the center word given a context word. And parameters, it's basically the parameters are these two matrices, Wi and Wo. And then we applied, so we defined a cost function and we applied gradient descent. And when we took the derivative of the log likelihood with respect to VW, this was our update rule. So VW new is VW old minus alpha. Alpha is the learning rate. And then we have VC times minus 1 minus the probability of the center word given the context. Now we've seen that the denominator is very expensive to calculate. And why? Well, in order to define your word embeddings, you'll probably run to a few million of pages of internet. And that's not only that. Remember, gradient descent has several iterations, so you got to do this for each iteration. Expensive, and then you got to do it for each iteration. No need to tell you that it's not a very practical solution here. Now, we not only have VW as a parameter, we also have VC. So if we take the derivative of the log likelihood with respect to VC, we get a very similar update rule. You see, because it's all symmetric. So VC new will be equal to VC old minus alpha, and then 1 minus probability of the center word given the context. Alright, so this will be our update rule for VC. This is very similar. Alright, so now we're done with C-ball. What we're going to look at now is skipgram and see where we end up here. In skipgram, the center word is given and I try to predict the context words. So it's a very similar situation. You have a center word jumped, and here again this is your x, and x is a d by 1 vector, 1 hot encoded. This is again our hidden layer h, and here again we have our y. Now we have 4 y's. In order to keep things simple, we only gonna predict c plus 1. Y c plus 1 means over. This makes things a bit similar. Principally, you have 4 of these here, each representing a context word. But we reduce the problem to 1 context word. Alright, so we know that y is also a d by 1. This matrix is going to be d by p. This is going to be p by 1, and this matrix will be p by d. Alright? So here we are. Now we're going to start deriving the formula here. But again, this picture is very similar. So basically your y, so let me see here, h equals w transpose I times x. This is d by 1, so this should be p by d. And then we have y c plus 1 equals, so let me just change this here. I'm gonna put the same as the other one. So this is I and this is O, right? So we have that this is W0 transpose H. Yeah. Now W0 transpose again, what will this be? Well, it's going to be a D by P matrix because this is P by B, so I need to switch. Yeah, so this is going to go all the way to D, and this corresponds with the jth word. Yeah, jth word. Yeah, of context. Jth context word. Yeah, so we can call this VC. All right, VCJ transpose, and this H here we're gonna call VW. All right, so the formula that we get is exactly the same as in continuous bag of words, that y c plus 1 equals, yeah, is the activation of VC J transpose VW. And here again we're going to apply the softmax, so we have e to the power of VCJ transpose VW, and here we have again the sum over all context words, in this case all words of the vocabulary, of e to the VCJ transpose VW. And the sum actually goes over all these words, all these context words. So again, you see something very similar. So here if you define the cost function and you apply gradient descent, you're gonna get something very similar to this here. Yeah. So your VC new is gonna be your VC old minus alpha, and then 1 minus the probability of a context word given a center word. And VW is going to be exactly similar, is VW old minus alpha 1 minus PC given W. Alright, now here again, same issue. Yeah, this is expensive. Alright, so we need to find a solution to solve this if we want to make this thing practical. And the solution is called negative sampling. Negative sampling.